Hello my precious friends and welcome to our today's class. It is our second lesson on the 8th topic of Form 3 work, which is called heating effect of electric current. As usual, let me commence by giving the quote of the day, which states that it's not enough to just start. You have to keep going too. We shall discuss that quote at the end of our class today. So today we are looking at electrical energy and power, and before we discuss electrical energy, let's remind ourselves of the first time we interacted with the word power. So under the fourth topic of Form 3 work, which was called work, energy, power and machines, that is what that topic is covered within this particular channel. You can just check it out. So we said that in that topic we did say that power is defined as the rate of doing work. Therefore, here we are just specifying a specific type of power, which is called electrical power. So we can define electrical power as the work done in moving a charge per unit times. Therefore, electrical power will simply be equal to work done in moving a charge divided by the time taken for that particular charge to be moved from one point to another. So electrical power, which is denoted by capital P, will simply be equal to the work done in moving a charge, which is denoted by capital W, divided by the time taken to move that particular charge, which is denoted by small t. Therefore, from our previous lesson, that is under heating effect of an electric current, lesson 2, we did say that the work done to move a charge from one point to another can be given by VIT divided by time, where V is the potential difference, then I is the current, and T is the time taken to move that particular charge. Therefore, the work done will be equal to the work done, which is W, is VIT, then but power is work done over time, so this will be VIT divided by time. Of course, time and time will cancel out so that we remain with power as being equal to the product of the potential difference and the current. Therefore, power, electrical power, can be given by VI. Similarly, if we substitute the equation of Ohm's law, which was V is equals to IR, in our first equation, so where we have V, I want to substitute with IR, so the equation 1 will simply become power is equals to, so where I have V, I'm substituting with IR, so power will be equal to IR multiplied by I. Of course, where I is the current and R is the resistance of the material. So power will simply be equal to I times I. You will simply obtain I squared. Therefore, power will be equal to I squared R. So this is another format that we can use to compute the electrical power. Then also from the Ohm's law, which we learned under current electricity 2, which is also a topic that we covered under Form 3 work in this channel. You can as well scroll and search for current electricity 2, whereby we dealt with the Ohm's law. So from Ohm's law, or from the formula V is equals to IR, if we make current subject of the formula, I'll simply divide both sides by R, so that current will be equal to V divided by R. So current can be given by potential difference divided by the resistance R. So therefore, the equation 2 becomes, so I'm simply substituting the value of current with V over R in my second equation. Remember, the second equation is I squared R, that is power is equals to I squared R. So where I have I want to substitute with V over R, so this will become V over R, because it was I squared, so this will become V over R squared, then multiplied times R. Then of course, V squared, V over R squared simply means we square each and every term, or the term on the numerator and the denominator. So this will become V squared over R squared multiplied by R. Then of course, one R will cancel with one R, so that will remain with V squared over R. Hence, electrical power can as well be given by P is equals to V squared over R. Therefore, these are the three possible equations that we can use to compute the electrical power. So power can be given by VI, it can also be given by I squared R, it can also be given by V squared over R. So the choice of the formula to be used in a calculation depends with what is provided in the question and the demands of the question. For example, if you get a question demanding you to calculate the electrical power, then you are given voltage and current, then the first formula will be appropriate. If you get a question asking for the electrical power, then you are given the current and resistance, then this second equation will be appropriate. Then if you get a question given the potential difference and resistance, then asking for electrical power, of course the third formula will be appropriate. Then the unit for power is simply the watt, which is denoted by capital W. and the watt is equal to the energy change rate, that is the energy change rate, of 1 joule per second. So that is how we define a watt. So if you're asked to define watt, you simply say it refers to the energy change rate of 1 joule per second. So from this definition, we can clearly see that 1 watt will be equal to 1 joule per second. Why? Because remember, the unit for the work done is the joules, then the unit for the time is actually the second. Therefore, if we are talking of power being equal to work done over time, we are simply talking of the power, which is watt, being equal to the work done, which is joules, divided by time. So joules per second. Therefore, 1 watt is equals to 1 joule per second. That is the units of work done divided by the units of time. Therefore, 1 joule, that is 1 watt, is equals to 1 joule per second. Of course, if we use the laws of indices, joules per second can as well be written as joules second power -1. Then a larger unit of power is what we call the kilowatt. Then you just need to know that 1 kilowatt is equals to 1,000 watt, just like 1 kilojoule was equal to 1,000 joules. Next, let's look at an example of how we can apply those formulas. So example 1 reads that a house has 20 watt bulbs. So we just take the information, then 2 1,000 watt heater and 2 500 security lights. So if the appliances are running on 230 volts, calculate part A, the total power in kilowatt used when all are switched on. So if we switch on all the appliances, so we'll simply, to find the total power, we'll simply add the power consumed by each and every component. So we are told that the house has 20 60 watt bulb. So if each bulb is consuming a power of 60 watt, therefore 20 bulbs will consume 20 times 60 watt. Then again, plus the power consumed by 2 heaters. If one heater is consuming 1,000 watt, then 2 heaters will consume 2 times 1,000 watt. Then lastly, if one security light is consuming 500 watt, then 2 security lights will consume a power of 2 times 500 watt. Then of course 20 times 60 watt, you will get 1,200 watt. 2 times 1,000 watt, you will get 2,000 watt. 2 times 500 watt, you will get 1,000 watt. Then 1,200 watt plus 2,000 watt plus 1,000 watt, you'll obtain a total power of 4,200 watt. So that is the total power, that is in watt, used when all the appliances are switched on. But the question wants us to find the power in kilowatt. Of course, we know the SI unit for power is just the watt. So to convert into kilowatt, we use this relationship. We have said that 1 kilowatt is equals to 1,000 watt. Therefore, if 1 kilowatt is equals to 1,000 watt, what about 4,200 watt? So that will be 4,200 watt divided by 1,000 watt times 1 kilowatt, which will give us a power of 4.2 kilowatt. 4.2 kilowatt. Then part B, they want us to find the total current drawn from the main supply. Of course, because we have the total power and we are given the voltage, the most appropriate formula will be the first formula, because you already have P and we are also given V. So from power P is equals to VI. If we want to find the total current will simply be P total over V total. That is, I'm just making current to be the subject of the formula in this case. So P total is equals to V total times I total. If I make current subject of the formula, I'll divide both sides by V total, so that I total will be power total divided by potential difference total. Then the power total, we use the power in its SI unit. The SI unit is the watt, so that's why I'm using this particular value. So the current total the total current consumed will be the power consumed, which is 4,200 watt, divided by the potential difference through the appliances, which was 230 volts. So 4,200 watt divided by 230 volts, you'll simply obtain a current of 18.26 amperes. So that is the total current drawn from the main supply. Next, our second example reads that a hoist motor powered by a 240 volts main supply requires a current of 30 amperes to lift a load of mass 3 tons at the rate of 5 meters per minute. Calculate part A, the power input. So because we are given that the voltage that is required to lift that particular load is 240 volts, that is supply, then the current required is 30 amperes. We look for a formula of power that utilizes voltage and current. Then of course, from our previous slide, we have just said that power can be given by the product of voltage and the current being supplied. Therefore, the power input, because this is the current that is required to lift a load of 3 tons, therefore the power input will simply be given by the voltage of 240 multiplied by the current of 3 amperes. Therefore, the power input is equals to VI, which is equals to the product of the voltage, that is the supply voltage, which is 240 volts, multiplied by the amount of current which is required to lift that particular load, which is actually 30 amperes. So 240 volts multiplied by 30 amperes, you'll get a power input of 7,200 watts. Then part B, they want us to find the power output. So the power output simply, in this case, simply means the amount of power that is provided by this particular load of 3 tons, which is being moved at a rate of 5 meters per minute. So from the given values, we are given distance, we are also given time, so we can simply find the velocity, we are also given the mass. So we'll find for a formula of power which utilizes the mass, that is the mass, the distance, or the distance covered, or simply the displacement covered, and of course the time. Then from work, energy, power, and machines, and when we were discussing about power, we did say that power can as well be given by the product of force and the velocity of that particular body. You can just refer from our lessons under work, energy, power, and machines. We actually derived the equation of power, and we did say that power can as well be given by force, the product of force, and the velocity. Then we know that force is equals to the product of mass and gravity. Then velocity is simply displacement over time. Therefore, this will be equal to, the power can be given by mg s over t, where s is the displacement, t is the time taken in SI units, which is actually in seconds. So the mass that is being lifted is 3 tons. But we know that the SI unit for mass is actually kilogram. Therefore, we'll convert the 3 tons into kilogram. We know that 1,000 kilogram is equals to 1 ton. So what about 3 tons? So we'll have 3 tons divided by 1 ton multiplied by 1,000 kilograms. So 3 tons into kilogram will obtain 3,000 kilogram. That is, we have just converted the tons into kilogram, which gives us 3,000 kilogram. Then the gravity on Earth obviously is always 10 Newton per kilogram, multiplied by the distance being covered in this case is 5 meters, then divided by the time taken. Remember, the time taken, we are told it is 5 meters per minute. Therefore, it is taking a distance of 5 meters in 1 minute. It is covering the distance of 5 meters in 1 minute. But we know that the SI unit of time is actually the seconds. Therefore, we'll convert the minutes into second. So this one simply means 5 meters in 1 minute. Therefore, if you convert 1 minute into second, we know that 60 seconds is equals to 1 minute. So what about 1 minute? So we'll just have 1 minute divided by 1 minute multiplied by 60 seconds. Therefore, our time, which is 1 minute, will be equivalent to 60 seconds. So if you take 3,000 multiplied by 10 times 5 over 60, you'll obtain a power output of 2,500 watts. Then part C, they want us to find the overall efficiency, again under work, energy, power, and machines, which is a topic that we covered in this channel, that is under Form 3 work. I think it was around chapter 4. We did say that efficiency can as well be given by the power output divided by the power input, then expressed as a percentage. Therefore, efficiency will be the power output. We have already computed it as 2,500 watts. So we'll have 2,500 watts divided by the power input. We have already computed it as 7,200 watts. So divided by 7,200 watts multiplied by 100%, or we are simply expressing it as a percentage. So 2,500 divided by 7,200 multiplied by 100%, you'll obtain an efficiency percentage of 34 whole number 13 over 18%. So that is the efficiency of that particular machine. Then example 3 reads that a heating coil providing 3,600 joules per minute is required when the potential difference across it is 24 volts. So the first thing, we just highlight the values or the quantities that we are given. So first of all, we are told that a heating coil that is providing 3,600 joules per minute we know that joules per second, those are the other units for power. So if 3600 joules are being made in 1 minute, so if 3600 joules is equals to 1 minute, what about so that simply means that 3600 joules can be equivalent to 60 seconds, because we know that 60 seconds is the equivalence of 1 minute. Again, we are converting to the seconds because we know those are the SI units for time. Then we know that joules per second, those are the other units for power. So we did say that 1 joule per second is equals to 1 watt. So if 3600 joules are being made or are being consumed in 60 seconds, what about in 1 second? So we'll have 1 second divided by 60 seconds multiplied by 3600 joules. So the amount of joules used in 1 second, that is simply the definition for power, because power can be given by work done over time, which is simply the units for work done is the joules, the units for time taken is seconds. Therefore, if you take 1 second over 60 seconds multiplied by 3600 joules, you'll obtain a power of 60 joules per second. Remember, joules per second, we can as well write it as 60 watt. So now we have the power, which is 60 joules per second or 60 watt. Then we are also given that when the potential difference across it is 24 volts, we are also given V, which is 24 volts. Then they want us to find the length of the wire making the coil. So the length is unknown, given that the cross-sectional area is 1 times 10 power negative 7 meters squared. So that is simply the area or the cross-sectional area of that particular wire. And we are also given the resistivity as 1 times 10 power negative 6 ohm meter. So from the values given, they want us to find the length. Then under current electricity 2, which is a topic that we covered again under Form 3 work, we did say that resistance can be given by resistivity multiplied by length divided by the area. So based on the values that we are given the area, we are given the resistivity, we have already computed the power, we also have the voltage. Based on the values that we have here, so we need a relationship or a formula that relates the values that we have. And we said that resistance is equals to resistivity multiplied by length over area. So that simply means, because we are given the cross-sectional area, we are given the resistivity, that means if we find the resistance, we'll be able to substitute the values in this formula in order for us to compute for the length of that particular wire. So we need resistance. And because we are given power and we also have the voltage, we can easily find resistance using the formula power is equals to V squared over R. So if I substitute my values, power, we have computed it as 60 joules per second or simply 60 watt, which is equals to V squared. So V squared is 24 squared divided by R. Remember, this is a formula that we have just derived from our previous slide. So this will simply be, if I want to make 24 squared subject of the formula, so I want to multiply both sides by R so that I eliminate the fraction. So I'll have 60R being equal to 24 squared, will get 576. So if I want to remain with R alone, I'll divide both sides by 60. Therefore, R will be equal to 576 divided by 60, which gives us a resistance of 9.6 ohm. Now, once we have the resistance, we are also given the resistivity and the cross-sectional area. We can now easily find the length. So under current electricity 2, we did say that resistance is equals to resistivity multiplied by length over the cross-sectional area of that particular conductor. Therefore, if I make length subject of the formula, because that is what I'm asked to find, so I'll simply multiply both sides by the reciprocal of rho over A, which is simply A over rho. So if I make L subject of the formula in this particular case, I'll simply end up with length being equal to resistance multiplied by cross-sectional area divided by resistivity. So resistance, we have already computed it as 9.6 ohm. So 9.6 multiplied by the cross-sectional area of that particular wire, we were given as 1 times 10 power negative 7 meters square. Then divided by the resistivity, I was given the resistivity as 1 times 10 power negative 6 ohm meter. So 9.6 multiplied by 1 times 10 power negative 7, then divided by 1 times 10 power 1 times 10 power negative 6, will simply end up with 9.6 multiplied by 10 power negative 7. Then of course, from the laws of indices, if this term moves to the numerator, the power will become a positive. So times 10 power negative 6. Of course, 1 and 1 will cancel out. So that simply means that we shall remain with 10 power negative 7 times 10 power times positive 6. We'll get a total of 10 power negative 1, which will simply move our decimal ones towards the left hand side. So this will end up as being the length of that particular wire will be 0.96 meters. 0.96 meters. Lastly, I have an exercise here which I do recommend that you try at your own free time to gauge your understanding of the questions that we have just done. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that it is not enough to just start. You have to keep going too. So the quote is reminding us about the importance of being consistent in our actions. Most of us have a habit of giving up on our dreams whenever we encounter a minor obstacle. Recall that nothing good in life comes easily. You have to invest your time, you have to invest your energy, you have to invest your resources in your dream in order for it to come true. And lastly, recall that your success will always be directly proportional to your attitude and your effort. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. In case you know any student or anyone that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy. Until next time, this is Kind Tuition Academy. Thank you very much.